Welcome to Climate Now. I'm James Lawler. Today's episode is the first of several in which we will focus on the sustainable aviation fuel, or SAF, landscape. Over the course of the next several episodes, we will speak with experts from companies working to develop and scale various methods for producing SAF, as well as SAF buyers and policy experts. According to the US EPA, aviation counts for 12% of CO2 emissions from transportation and 2% of all CO2 emissions globally. Sustainable aviation fuel, or SAF, is aviation fuel made not from petroleum hydrocarbons, but from other sources of carbon and hydrogen. These sources include non-fossil hydrocarbons, such as waste oils and other kinds of oil derived from plant material, and more complex sources like woody biomass and even municipal solid waste. Perhaps the most intriguing source of carbon that could be converted into SAF is the CO2 in the air itself, a supply that's practically unlimited, but is by far the most expensive to access using today's technology. Each of these feedstock sources can be converted into SAF using a different technological approach. HEFA, which stands for hydrotreated esters and fatty acids, is a process that involves adding hydrogen to waste oils. Alcohol to jet uses feedstocks like corn or sugarcane to produce sugars, which are then fermented into alcohols, think ethanol, further processed and hydrogenated or combined with hydrogen to make jet fuel. Gasification, paired with the Fischer-Tropsch process, uses high-temperature gasifiers to break down sources of carbon like municipal solid waste and biomass, while power to liquids refers to the use of direct air capture to capture CO2 molecules from the atmosphere, and electrolysis to produce hydrogen by running electricity through water. The CO2 and hydrogen can then be combined using a variety of catalysts to make SAF or other hydrocarbons. When thinking about the challenge of making sustainable aviation fuel, the key principle to keep in mind is that it's about building chains of carbons and hydrogens. Jet fuel has a 12-carbon chain. CO2 is a single carbon. So to make jet fuel, you need to break apart 12 CO2 molecules and get the carbons to join into chains with hydrogen. You need lots of energy to do that, energy that the airplane will later use to take off and fly around the world. Starting from oils, as the HEFA process does, starts you part of the way there, and so less input energy is needed to get to SAF. But the catch is, for HEFA, that there's a lot less feedstock available. We'll get into all of these issues, pros and cons, challenges and opportunities, over the course of the next few conversations. To step back a bit, approximately 160 million gallons of sustainable aviation fuel were consumed in 2023. Now, this sounds like a lot, but it's actually really a drop in the bucket compared to the nearly 90 billion gallons of petroleum-derived fuel that airlines consumed globally in that year. But compared with conventional fossil jet fuel, SAF emits significantly less CO2, more or less depending on how you make the SAF, so its widespread use would be a significant step forward to decarbonizing aviation. For those new to the topic of SAF, it's important to understand that most of the time when we talk about SAF, we're talking about a drop-in fuel, meaning a fuel that can be used without needing to modify the engines that are running on conventional jet in any way. It's simply a replacement fuel. When you burn SAF, you emit roughly the same amount of CO2 as you would burning conventional jet. The key, of course, is that the CO2 originally was in plants. So, on a net basis, you're releasing no new CO2 into the atmosphere. My guest today is Beatrice Batty of Epic Fuels, which is the fuel supply division of Signature Aviation. Beatrice is an expert on all types of aviation fuel, including sustainable aviation fuel. Welcome, Beatrice, and thanks for joining us.
Thanks for having me, James.
So, Beatrice, tell us about your role with Epic Fuels. One is Epic Fuels, one is Signature Airlines, I believe.
Signature Aviation is our overarching corporate parent company. We provide high-level service and all of the various support services that an aircraft that lands at any airport needs. A big part of that is fuel. So we have aviation fuels that we offer to those customers, and that's what Epic Fuels does. My role at Epic Fuels, I'm Director of Fuel Planning and Risk. So I and my team are responsible for our long-term strategic approach to fuel supply, as well as our contracts with fuel suppliers. And that's for avgas, unleaded aviation fuel, jet fuel, and of course the topic today, sustainable aviation fuel, or SAF. So we get all of the fuel that we can through contracts. Our company also has a logistics wing where we contract with rail entities and trucking companies to bring the product to the airport itself. And that's our role in this world, is to get aviation fuel to the airport for our customers so they can sell it to the end user, who are the aircraft operators.
Can you tell us how many gallons per year of aviation fuel Epic buys and sells?
We have a portfolio of customers that we end up supplying them with upwards of 500,000 or more gallons per year of various. And that is a large task because we do that across several hundred different distribution points.
Wow. The topic du jour is sustainable aviation fuel. How does it differ from traditional aviation fuel that we run planes on?
So traditional jet fuel is made like all petroleum products, taking crude oil, putting it through a refining process and breaking it down to different subproducts, including jet fuel. Sustainable aviation fuel is the same chemical at the output, in that it is jet fuel, but it's not made from crude oil. It's made from another more sustainable feedstock. And the intent is to lower the ultimate carbon intensity of the jet fuel that's being put into aircraft. So carbon intensity is, actually, I should restate that. It's a life cycle carbon intensity. And that is a calculation of the entirety of that product, from obtaining the feedstock, processing it into fuel, whether it's crude oil into jet fuel or another feedstock with sustainable aviation fuel, bringing it to market, and ultimately bringing it to the airport where it's pumped into an aircraft, and then that aircraft burns that fuel. In all stages of that life cycle, there's carbon emission. And we can compare the life cycle carbon intensity between a sustainable aviation fuel and standard jet fuel from crude oil. The difference between the two is how we rate or catalog the reduction in carbon that's emitted into the atmosphere from the product.
So let's dive into SAF and look at the different pathways for producing it that are feasible today. Could you walk us through the methods that are being explored today?
There's multiple different chemical pathways that are approved today and those that are being worked on to be approved. That generally means it's just a different chemical process to take one of these sustainable feedstocks and turn them into jet fuel. And how you do that depends on what that feedstock is. There's three general categories that we look at. So there's fats to fuels, there's waste to fuel, and there's air to fuel. And there's a couple of subcategories underneath that. In fats, it's a process called HEFA, or hydroprocessed fatty acids. You're taking a product like tallow from animal processing, used cooking oil, and some other oils that have a high fat content. You're chemically processing that larger hydrocarbon molecule in that fat down to a smaller molecule so that it creates something identical to jet fuel or other renewable fuel products. So that's the first one.
Give us a sense of the technical challenges associated with HEFA.
This is low risk, and today commercially scaled volumes being produced. It largely capitalizes on existing refining technology. It's adding a couple steps after you refine oil or the feedstock itself. So we're seeing that as the first place we're getting SAF, because it does capitalize on existing technology to be able to produce the sustainable aviation fuel. All of these fuels have to be blended with jet fuel so that you have a product that can actually be put into the aircraft. It's an essential step to blend it and to recertify it as actual jet fuel so that you can get it to the aircraft.
So, Beatrice, who is making sustainable aviation fuel through the HEFA process today, and how much are we making globally?
The several producers out there that are making SAF through the HEFA process. The largest companies that are doing that today are Neste and World Energy. Other traditional refiners making some in smaller batches are also ramping that up now. They're converting over to doing sustainable aviation fuel. What's interesting and important to note here is the process to make sustainable aviation fuel is very, very similar to making renewable diesel. So when you're talking about an existing refiner, such as Valero, Phillips 66, Shell, and many others, they're making both diesel and jet fuel today. And it's the same with producing SAF. It's a close cousin chemically. So a lot of these larger oil refiners are making renewable diesel today. They've actually been putting out quite a bit of that product over the last several years. But we're starting to see them convert more to making sustainable aviation fuel in that same process. And that's economics driven. We're seeing more and more of the larger refiners bringing SAF to market, as well as those dedicated to SAF, such as World Energy and Neste. it is a small fraction of total jet fuel production. There's nobody actually counting the number of gallons or molecules being produced in SAF today. You can go out online to government websites and find how much jet fuel was consumed last year quite easily, but nobody's actually tracking SAF. Right now, the best estimate is less than 1% of the total jet fuel demand is in SAF. So we're talking a couple of 100 million gallons compared to the billions that you quoted earlier. So we're ramping that up. More people are bringing more production online every quarter, but we're still in a very small percentage today.
So do you think, Beatrice, we're at hundreds of millions of gallons already with HEFA production?
In the total blended gallon, yes, we are in the hundreds of millions. And so let's define this a little bit. When we talk about production of sustainable aviation fuel, the term that everybody uses is neat SAF. So you think about whiskey without any ice in it, right? Neat, as opposed to on the rocks. The number of gallons produced for neat SAF is, yes, less than 100 million in the last couple of years. As I mentioned earlier, it's imperative to blend that with traditional jet fuel and then recertify the product to make sure it meets all of the chemical standards of jet fuel. Right now, the most common blend ratio is about 30% neat SAF with 70% of fossil-based jet fuel. And it varies. So if you produce 30 million gallons of neat SAF, you're going to be at about 100 million of blended SAF, which is actually able to be used in an aircraft, probably. We are in the hundreds of millions on the blended SAF, but I think by 25, 26, we'll cross into 100 millions in the neat SAF as well.
Just to dive a little bit more deeper on HEFA. So you mentioned feedstocks are tallows, they're used cooking oils, so they're different fats that are residues from our food system, essentially. Where are the companies that are producing the SAF getting these fats? Is McDonald's selling all of their used oils to a fuel producer today?
Yes. There are large-scale food producers that are selling their used cooking oil. Tallow is actually a product that's a commodity-traded product and has been as a byproduct of the food industry for many years. You're right in that it's generally waste products because we want it to be as sustainable as possible. So yeah, this is a whole sub-industry of getting feedstocks for production of various renewable fuels. The challenge with HEFA specifically is the amount of SAF that we have to produce to meet that goal by 2050. There's not enough feedstock to be able to use HEFA alone to get us to that goal, because it is used in other industries and in other production technologies as well. So HEFA by itself won't get us to that goal of net zero in aviation because of a limitation on the amount of feedstocks. It is a challenge to go and collect all this used cooking oil or tallow from production facilities and bring it to a production plant.
Any sense, Beatrice, on the total capacity of the HEFA process when it comes to SAF production?
I don't have a great number. What I do know is we're probably talking less than a third of the total that we would need in SAF.
So let's move to the next category. So this is waste. I believe it was waste to fuel.
Waste to fuel. That's correct. Yeah. And there's two subsets under this. There's alcohol to jet, and then there's gasification Fischer-Tropsch. Both are using a slightly different feedstock. The gasification or Fischer-Tropsch process uses, believe it or not, my favorite is municipal solid waste, only because of the shock values. People think, well, wait a minute, I can take the landfill that my town has and turn it into jet fuel. The answer is yes, you can. And the other is alcohol to jet, which uses ethanol primarily, which again is a waste product from other productions, whether it's sugarcane or corn production. And they each have their pros and cons. And that's what I call our second generation of sustainable aviation fuel that's going to be coming to market.
So drilling in a little bit deeper on these. So the gasification of Fischer-Tropsch, basically you're putting in this feedstock and heating it up and producing syngas. So what are some of the limitations of that process when it comes to taking waste streams and converting into fuel?
With the feedstocks that exist for this particular chemical pathway, municipal solid waste, woody biomass, which is residue from the forestry industry or fall, these are a solid that has to be processed down to a raw carbon molecule or carbon substance that can then be converted over. Probably the biggest challenge is how do you clean it? How do you get it down to something that's just a pure carbon product that can then be converted over? And when that happens, you still always have some residue you don't want to chemically convert over to SAF. So there's a constant process of having to go back, literally clean out the gum in the works, so to speak, to bring out a pure SAF. The other challenge is you're getting smaller amount of feedstocks locally. So your ultimate output would naturally be smaller outputs, and you'd have to have more of these production facilities to get the same output as you could in a large, say, HEFA, where you're bringing in a very easy and already well-worn path of bringing in a feedstock that can be shipped via rail and barge and be able to process on larger quantities. So those are the two challenges we see with that particular chemical pathway.
And is there anyone doing this today?
There are several people that are working through getting the test projects and a sustained and scalable volume. The one most notable is Fulcrum. Fulcrum's been working with a municipal solid waste process, and they have a test production right now that is putting out some products. In all of these second and third generations, nothing is scaled right now for those commercial levels. They're in test production.
We've spoken with an engineer who's familiar with these gasification systems. When we said gasification, his reaction was, don't say that word to me. Gasification is notorious for this tarring effect because of gasifying a very diverse feedstock mix that you can't control. Some believe that this is a really significant engineering challenge to get this right.
That's correct. It's the actual feedstock itself that creates a complexity to be able to get a consistent output that can be scaled up to commercial levels. There are many projects out there. It's an old process, and they continue to work to get this refined and find better ways to do it. I spoke with one new producer that had a newer process to be able to take in municipal solid waste. And when I asked, how are you sure that you can get to a scalable production when we're talking about something as varying as municipal solid waste? His answer was higher temp. But again, that in itself creates problems in maintaining long-term production. The higher temp wears down all of the various components and parts within that process.
Right. We did speak with one producer of these gasification systems that has an ability to really jack up the temperature to make that uniform. It's an experienced team. They've been around the technology as long as anyone operating in the space and are very, very bullish on being able to do this. So again, we'll see. It's exciting times.
Right. While there are challenges to every one of these technologies, I actually am optimistic that we will tackle most of them. I really believe that we need multiples of these technologies and feedstocks to get aviation to truly be at net zero.
So let's move to alcohol to jet.
Yes. So similar to the olives, we're taking a byproduct of something else, and that is ethanol. We're looking for that, sugarcane, corn oil, and some others that will ultimately produce an ethanol product. And you're doing the same thing. You're breaking down and reprocessing that molecule into a different molecule or smaller hydrocarbon chain. This has the benefit that the actual feedstock is a cleaner and a more consistent feedstock. The actual carbon intensity or the improvement in the carbon output of this product is a little bit on the higher side compared to, say, a HEFA. The aviation industry standard, their program called CORSIA, defined average life cycle carbon intensities of all these various feedstocks. The baseline for that is fossil-based jet fuel, which is 89. The life cycle carbon intensity for HEFA is generally 22.5, depending on the region and the actual feedstock. So in the United States, if you're using tallow, use cooking oil, and using a HEFA process, the CORSIA identified life cycle average is 22.5. But with an alcohol to jet, it's about 50. So not quite as much carbon reduction. And you also lose more output product using the ethanol feedstock. So for every gallon of ethanol you're using, you're producing less actual neat SAF on the output than you are with the HEFA process. So you need more feedstock. So those are the challenges on that, but it'll be easier to scale this. I think in the next few years we'll get commercial scaled volumes out of the alcohol to jet process.
Beatrice, just to clarify, how does the life cycle carbon intensity of neat alcohol to jet fuel compare with the carbon intensity of fossil jet that it's blended with?
So the neat is at a 50 compared to 89 if it was just straight fossil jet. But when you blend that at a 30% SAF and 70% fossil, it's around a 22 to 25% reduction in life cycle CI for the blended product.
How will airlines meet their goals of net zero operations in a world where you have to blend at a 30-70 ratio with these fuels? Even if you did have a SAF with a score of 0, you're still blending 30% zero with 70% full fossil fuel.
Right. It's a journey, right? And there's several different strategies to get there. To start off with, we work with a lot of original equipment manufacturers, both engines and airframes.
Mm-hmm.
They're all testing neat SAF and getting to a point that their products, that the aircraft and the engines that are being used can accept neat SAF. So that's a number one technical hurdle we have to get to, that we won't have to blend it long term. The various regulatory bodies like the FAA in the United States, they're looking for those airframes and those engines that require the blending to sunset. We have to get rid of that equipment. That's going to take a couple decades. But in the meantime, we'll have new equipment coming on board that can use a full 100% SAF. The other area is carbon sequestration. We see that the waste carbon coming off of the production can be captured or sequestered in some way that'll bring the ultimate CI down lower. There's a couple of different calculation models that take into account the carbon sequestration to say that you've actually got a 0 or a negative score CI for a particular product. And different ways we're going to get there. Once we get to the last technology, power to liquid, that in itself is going to have much better CIs and will be a great step in this journey to get us to negative 0. In the meantime, it's going to be using traditional offsetting models and other ways to reduce your carbon footprint to get there. Our company is doing that right now, in that we are finding ways to reduce our carbon footprint, not just in the SAF that we sell, but also in the electricity we use, and trying to install more solar panels on our facilities. And those are helping reduce our larger footprint.
I'm glad you touched on this notion of offsetting the carbon footprint. There's a voluntary carbon market for the purchase of carbon removals from a wide range of providers. These projects range from direct air capture projects, where you can literally measure the amount of carbon that is going underground or is being captured in some sort of permanent form. So the quality of that offset can vary dramatically. The markets are somewhat opaque, but it could be at some point a viable strategy to offsetting emissions from fuel.
I don't want to speak for an airline, as that's not our business, right? We are a service provider to airlines and to operators. However, what I've seen in many of these companies, the company itself has made a sustainability goal. So they're looking at different strategies to make that happen. There have been some programs that have called into question if they're true carbon offset. And we are seeing more rigor around this process to make sure that the programs are valid, that they do what they say they're going to do. And I know with our process internal with Signature Aviation, our approach to SAF is the same. And the interesting thing is most of our customers are looking for the same thing. The approach is fairly sophisticated amongst most of them. They're looking at, how do I actually calculate the kilograms or tons of CO2 that I'm reducing? And then how do I plan to reach that?
A couple of minutes ago, Beatrice touched on what is arguably the holy grail of technologies for making sustainable aviation fuel, and for that matter, any hydrocarbon: power to liquid, or PTL. PTL would use renewable electricity, most likely from solar power, to electrolyze water, producing hydrogen that is combined with carbon dioxide captured from the atmosphere or industrial processes to produce sustainable aviation fuel or other hydrocarbons. Its CO2 removal aspect means that power-to-liquid SAF would come close to being carbon neutral. In 2021, the Air Transport Action Group, an industry organization, predicted that PTL-produced SAF will account for 42 to 57% of total SAF by 2050. So let's talk about maybe the least carbon-intensive pathway, which is the power-to-liquids or air-to-liquids fuels pathway. How does it work?
Sure. This is probably the gold standard that everyone's trying to reach, right? It's the true magic in chemical processing, I guess, taking CO2, a waste product from a lot of different industrial processes, and building it to the chemical that you want, in this case, sustainable aviation fuel. This process, however, requires a lot of green hydrogen and green power to make that happen. You start with a very pure feedstock, CO2. you end up with a really great carbon intense or lower carbon intensity product at the end. But the process needs this green energy. There's not enough green energy today to power the processing plants that you would need to bring 100% liquid SAF to market. I am aware of a couple of projects that are in the test phases of this. They're generally bringing out different products, not SAF just now, to test the technology and find the right ways to scale it up.
Now, where does that CO2 come from? It comes from direct air capture systems, which themselves have to be powered by massive amounts of power because they're capturing CO2 molecules from the atmosphere, where CO2 is only 400 parts per million. That takes a lot of power, and then combined in a synthesis process with this hydrogen to make your fuel. There's only so many places we can do this. Now, the proponents of this, and there are some that are very eloquent on power to liquids and will say that we're going to have plenty of solar, and we actually don't need to tile every square foot. We have plenty of land in this country and plenty of sunlight hitting that land to produce more than enough solar to do this at scale.
When we look at what they're actually going to be producing in the near future, power to liquid has always been discussed as something that's 10 to 20 years away. And that's probably still accurate, even though there's test production facilities now, in terms of getting a scalable product that really does deliver the low carbon that they're talking about. The positive of this is these test facilities are working through the technology and working through the challenges of getting the green energy, the green hydrogen that they need.
We've talked about different technologies. We've talked about some of the challenges with those technologies, but in your world, you look at more than just technology. You look at logistics. How do you actually get these molecules from the points where they're produced to the aircraft? What are some of the things that maybe people overlook about actually selling the stuff and getting it into airplanes?
I'm glad you asked me that question, James, because I see that as one of the bigger challenges we have in the next decade or so. I mentioned earlier that the product right now needs to be blended with regular fossil jet to make it chemically identical to meet the ASTM standard for jet fuel. That's also imperative from the infrastructure. Right now, we use a myriad of ways in which we move jet fuel from its production to the airport to move it into the aircraft. It's moved via rail, truck, pipe, or barge to another storage facility that's close to the airport, then moved again in some other manner into the airport itself. Then it's put into an airport storage. Right now, SAF in its neat form meets the chemical standard of ASTM 7655. That's not jet fuel. So the most efficient thing to do is to take the neat product, blend it someplace where it makes sense to be able to then distribute it as jet fuel through those traditional means that exist today. So now the challenge becomes, how do I get their neat product to an existing jet fuel infrastructure? Obviously, any movement increases the carbon output of that product. So that's a step that we have to look at as an industry as well, is how do we maximize the efficiencies of the production to the airport itself? And that's a challenge that I don't think we've completely solved yet. It's another one of those journeys or pathways that we're going to have to follow in parallel with getting more of these production facilities up and running.
This conversation was our first in a multi-part series of episodes on sustainable aviation fuels. Upcoming interviews will feature Brooke Coleman with the Advanced Biofuels Business Council, Bruce Fleming, the CEO of Montana Renewables, and Stéphane Thion of LanzaJet. To read the transcript or find sources for various statements made in this episode, visit climatenow.com. We hope you'll join us for our next conversation. Thank you.